Hi everyone, happy Wednesday. Welcome to the Chem Help ASAP live stream for tonight. I should say today. Today we are going to be talking about mixtures, and we're talking about different kinds of mixtures as well as pure substances and how all of these words kind of fit into a chemical meaning. So let's go ahead and get started. Let's get some definitions and then we'll practice identifying some pure substances and some mixtures. Okay, so first, just to get our language correct here. First of all, matter. Matter is anything that occupies space and has mass. So the great chemistry joke is you matter because you occupy space and you have mass. So that is first the definition of matter. Now, matter can be classified in two different ways. So we can either classify it as a pure substance or a mixture. Now, first, I'm going to focus on the pure substances, and then we will focus on the mixtures. Okay, so pure substances. Pure substances can be broken down into two different categories. So pure substances can either be an element or a compound. All right, so let's focus on an element. An element is composed of only one type of atom. So you can see here, I've got a picture of some gold rings. Presumably these are pure gold rings. That means they're made up of one type of atom. They're made up of the gold atom, and that is it. There are no other atoms that are a part of that. Now, I do actually have I don't know if you can see this online. This is a copper ball. Now it's got a bit of a patina on it, but this ball is made of pure copper. It is an element. It's made up of one type of atom. Now, I guess I couldn't have fit this on here. When you think about elements, you probably think about the periodic table of elements. And this is correct because that gives you all of the different elements. So if something is an element, it means it is in its pure form. Again, only one type of atom. Now, we're going to contrast that with a compound, which can also be pure. But a compound is composed of two or more elements in fixed definite proportions. So a classic example of this, you can see my glass of water. Water, as we know, is H2O, which means you have two hydrogen atoms for every one oxygen atom. That's what we mean by fixed definite proportions. So for example, if you have pure water, you are not going to have H3O, which actually has a plus sign. Nope, because that is a different proportion than water, which is always H2O. You're also not going to have, say, HO, which would really write as OH, that has a negative charge, because again, that is a different proportion. That is a different substance. It's actually an ion. So this is what we mean by a fixed definite proportions. This is all water, H2O, and we're not changing up any of the proportions. But these can both be pure. So for example, I'm to make sure I can see this. I don't know if you guys can see this. Maybe I'll hold it like this. I've got a little plastic kitty cat here, and this is pure plastic. So it is a pure substance, but of course it is one or more elements bound together, but it is in a fixed proportion. Okay, so that is what it means to be a pure substance. It means you're either an element and you're one type of atom, or if you're more than one element, you are in a fixed definite proportion and you don't have a mixture of things going on. With that being said, let's talk a little bit about mixtures. All right, so just like we divided pure substances into two different categories, we are dividing mixtures into two different categories. So first we're going to talk about heterogeneous mixtures. So a heterogeneous mixture, just like hetero implies, you've got two or more compounds, but the composition is going to vary throughout the mixture. So for example, I had this picture of boba tea. So imagine if you have boba tea and you wanted to give somebody a taste. Well, if they took a taste from the very top portion of the tea, they would only get the tea and they wouldn't get any of the tapioca balls. But if you gave them a taste from the very bottom portion, maybe they would get all tapioca balls and not very much tea. So the composition changes throughout the mixture. So that is a heterogeneous mixture. And you can see the difference in the mixture. As opposed to a homogeneous or homogeneous, you hear it pronounced both ways. Now this type of mixture still, again, two or more compounds are mixed together, but the composition is the same throughout the mixture. So here we have an example of some hot tea being poured. And once this cup is full, it wouldn't matter if I took a sip of tea, if I could, from the bottom of the cup versus the top of the cup. It would still be tea. It would taste the same. It would look the same. It would have the same composition. So again, a heterogeneous mixture is going to vary throughout the mixture, and a homogeneous mixture is going to look very uniform, and you're not going to be able to tell, oh, here is a tannin in the tea molecule. Here's a little bit of sugar that I dissolved in. It's all going to be very uniform throughout the whole mixture. Okay, so these are pretty much our vocabulary words for dealing with pure substances and mixtures. So let's put this into practice and let's actually run a problem, and we're just going to talk about a bunch of different situations and compounds and mixtures, and we're going to identify things. So for this problem, we are first going to classify each type of matter as either a pure substance or a mixture. So that's always the first thing. Is this a pure substance or a mixture? Once we have identified it as a pure substance or a mixture, we're going to go a little bit deeper. So if we identify it as a pure substance, we're going to identify it as either an element or a compound. If we identify it as a mixture, then we're going to classify it as either a heterogeneous or, okay, so it looks like my homogeneous mixture got cut off there. We're going to classify the mixture as either heterogeneous or homogeneous. So we're just going to get really specific with all of these different examples. Okay, let's jump in. We've got A through N, so we've got a lot of things to discuss here. Okay, so our first one here is seawater. All right, so if I go to the beach and I take my little bucket and I scoop out a bucket full of seawater and I look at it, is it first a mixture or a pure substance? Well, if you think about seawater, there's a lot of water in it, right? But there are also other things. So there are a lot of salts dissolved in seawater. It is not just pure H2O. It has other things in it. So seawater first is a mixture. Okay, so let's think about if it's going to be a heterogeneous or a homogeneous mixture. So if I were to look at that bucket of water and take, again, a sample from the bottom versus the top, or like the left side versus the right side, would it be the same? And yes, assuming you didn't like scoop up sand with it. So I'm just taking the seawater, not any of the sand, or, assuming you didn't get a fish in there too, then it would be the same throughout. So seawater is going to be a homogeneous mixture. Now, an interesting twist you can put on this is if you were to take a sample of seawater, say from in the waves where everything has kind of been mixed around, then you might get some sand mixed in with the seawater. Well, that would still be a mixture, but that would be a heterogeneous mixture. So it's kind of interesting to think about these different things and think about various scenarios and go, well, I could make this a heterogeneous mixture if I did this in a specific way. Okay, so seawater, we're going to classify that as let's not do that in red, as a homogeneous mixture. Mixture. Okay, now let's go on to B, distilled water. So if water is distilled, it means it has been purified. Okay, so first of all, is this a pure substance or a mixture? Well, the fact that it's distilled means it has been purified, hence that it is going to be a pure substance. Okay, so then the question is, if it's a pure substance, are we talking about an element or are we talking about a compound? And of course, water, like we just talked about, is H2O, so it is two elements bound together, three atoms, two different elements. So this is going to be a pure compound. Okay, on to C, just air, just in the air around us, the atmosphere around us. Is this a pure substance or a mixture? This is kind of a classic one that you see in these kind of questions, and most of the time students want to classify this as a pure substance, but actually it is a mixture. So you have in air, you have a mixture of gases. Now it's mostly nitrogen, but obviously it's got some oxygen in it and some other things. So air is a mixture. Now, if you kind of look at the air around you, can you tell the difference? So if you were to take, a sample of air from over here or a sample of air from over here, would you be able to tell that there's a difference? No, it all looks very much the same. So air is going to be a homogeneous mixture. But again, you could think of taking a sample of air, say, from a city that has a lot of pollution or a lot of smog, and then maybe you could see that there is a difference in the mixture if there are a lot of particulates in the air. So again, it's kind of cool to think about, all right, so air is generally a homogeneous mixture, but again, you can think about situations where maybe air would be a heterogeneous mixture. Let's make sure there are not any questions here. Okay, good. All right, so let's just keep on rolling here with this. Okay, so D is chicken noodle soup. Now, this might be a very American thing, I'm not sure. But chicken noodle soup is a broth, and it has bits of chicken and bits of noodle in it. And it's something that, at least for me, traditionally, you had when you were sick, your mother would make you chicken noodle soup. Okay, so first of all, is this a pure substance or a mixture? Well, it does have a broth in it, but again, you've got obvious bits of chicken and noodle, so this is going to be a mixture. And again, because these bits are obvious, this is definitely going to be a heterogeneous mixture. Okay. Sticking with the soup here. Now we're asked about tomato soup. This can kind of depend on the situation, but I am assuming you're working with like tomato soup, then you've made it out of like a condensed, like a can of soup. So if you think about tomato soup and you're mixing it, again, is it a pure compound or is it a mixture? Well, it is a mixture of water and all of the different chemical compounds in the tomato. So yes, it is definitely a mixture. Now, is it uniform throughout? Well, again, assuming you're making it from a can of condensed soup, then that is going to be a homogeneous mixture. So we'll go ahead and put that down here. But I have also had tomato soup that is more homemade and it maybe hasn't been pureed as much, and it will have little bits of tomato in it. So that could be a situation where you have a mixture, yes, but it's actually more heterogeneous if you add in those chunks of tomato. Again, a lot of these things you like in this kind of problem here, you assume a certain scenario, but it's kind of cool to think about, all right, how could I change this? Could I make this homogeneous mixture heterogeneous, or could I take this heterogeneous mixture and make it homogeneous? Okay, but on to F, sugar. All right, so sugar, first pure substance or mixture. It's definitely not a mixture, but it is. So it is a pure substance, assuming you've got just a bag of pure sugar. But is it an element or is it a compound? Well, sugar is a mixture of carbons and hydrogens and oxygens. So definitely it is going to be a compound. Another thing you can do is if you look at the periodic table, there is no element known as sugar. So sugar is going to be a pure substance, but it is going to be a compound. So we'll say it is pure, but it is a compound. Okay, next up we have baking soda. So we've kind of been in the kitchen here for a little bit with some soups and some sugar and some baking soda. Okay, so baking soda first, pure substance or a mixture? Nope, baking soda is definitely a pure substance, but is it an element or is it a compound? Well, baking soda is actually a mixture of sodium and hydrogen and carbon and oxygen. So it is a compound, but it is pure, so this is a pure compound again. Now, this is assuming that you're not mixing like baking soda with baking powder. That would be a mixture of two different compounds. They're very similar, but two different compounds, and that would be a homogeneous mixture. But just baking soda is going to be a pure compound. Okay, so H is copper. Oh, that's very much, it's like my little copper ball here, right? So copper, pure substance or mixture? Well, copper is a pure substance. Is it an element or is it a compound? Well, you can find copper on the periodic table. Its atomic number is actually number 29. It's kind of in the middle there. So copper is an element. We'll call this a pure element. Okay, next we've got bronze. Okay, so you do have to know a little bit about what bronze is. So is it a pure substance or is it a mixture? So bronze is actually copper with a little bit of tin in it. So automatically that tells us that we've got a mixture going on. So these are not, it's not a copper bonded to a tin atom. They're just mixed in together. So it is a mixture. Now then the question is it homogeneous or is it heterogeneous? Well, if you think about bronze in, say, a musical instrument or in any kind of jewelry, you'll see that it's very uniform throughout. So bronze is a mixture, but it is a homogeneous mixture. It would be the same thing for brass. So brass is copper and zinc, I believe, where bronze is copper and tin, but they're both mixtures and they're both homogeneous mixtures. Okay, we're almost done with this. Okay, so let's go on to J, gasoline. Oh, this one is a little bit tricky. So it kind of depends on how much chemical knowledge you actually have. All right, so gasoline is obviously a product that is made from the refining of crude oil. And it is actually a certain set of compounds. So gasoline is a mixture. Now, if you have a can of gasoline, can you tell like where the mixture starts or stops? No, you can't. It's definitely homogeneous or homogeneous. So this is a homogeneous mixture. But you could also think of gasoline as octane. And if you think of it as octane, just pure octane, that would actually be a pure substance. But here in this problem, I'm assuming they mean gasoline like what you would put in your car. And it is a little tricky because you have to understand how, at least have some understanding of how crude oil is refined. But gasoline is actually a mixture of compounds. So, you know, TIL. All right, let's go on to K. K is a chocolate chip cookie. So there are a lot of kitchen things here, and thinking about the cookies making me a little bit hungry. Okay, so a chocolate chip cookie. Is this a pure substance or a mixture? So if you think about a chocolate chip cookie, or if you've ever made chocolate chip cookies, you know that you put a lot of different ingredients into the chocolate chip cookie. So it's definitely a mixture of various ingredients. Okay, so now we have to think about, is it a heterogeneous mixture or is it a homogeneous mixture? Well, hopefully your chocolate chips remained intact, right? And you didn't just make chocolate cookies, but chocolate chip cookies. And that would be a heterogeneous mixture. A very delicious heterogeneous mixture. Oops. Okay, my pen is not really writing very great tonight. Okay. L, platinum. Okay, so this one is something that you do find on the periodic table, so that kind of gives it away. So you might have like some platinum jewelry. So platinum is a pure substance, and it is one type of atom. So it is going to be a pure element. But kind of like copper does and a lot of other things do, platinum will form a little bit of a patina on the outside where it reacts with the air. And so you could argue that if you have a piece of platinum jewelry and it has formed a patina, that you actually have a heterogeneous mixture because you've got a little bit of that oxide on the outside. But we're just assuming pure platinum here. Okay, so we're almost done here. We have soil. Now this one is a little bit tricky. So let's first go pure substance or mixture. So if you think about going to get a soil sample, obviously you do have a lot of different things in soil. You've got different salts, you've got different organic compounds. You might have like roots or bugs or anything like that. So it's definitely a mixture. Now you could think about the different kinds of soil. So if you're in an area with really sandy soil and you take a soil sample, it might be really close to homogeneous or homogeneous. But most soils, if you dig a soil sample, you can see that there are different layers in the soil. So most soils are going to be heterogeneous. But they are definitely a mixture of different compounds. Okay, so our last one is cola. This could be any cola you like. And so this is one where, okay, is it a pure substance or a mixture? Well, cola is definitely a mixture. If you look at, your can or your bottle, you'll see a whole list of different ingredients. But again, if you pour yourself a glass of that cola, would you be able to tell, like, if you used a straw and you took a sip from the bottom or you took a sip from the top or midway through? No, it would all be very uniform. This is a homogeneous mixture. Now, again, just to play devil's advocate a little bit here, if it's very carbonated and you have a lot of the CO2 being released and you can see the bubbles in there, you could argue that the cola, as long as it's not flat, might be considered more of a heterogeneous mixture because you say, hey, I see these little bubbles of CO2 that are escaping into the atmosphere. So again, with all of these things, there's always a little bit of wiggle room, especially with the mixtures. Now, the pure substances, the elements, and the compounds, like those are pretty well set, but it's kind of cool, again, to think about the mixtures and think about, again, is it heterogeneous? Is it homogeneous? How could you think of a situation where you could maybe flip-flop it? Okay, so any questions on this? No, looks like we are good. All right, so the last thing that I want to talk about, since we've kind of been talking about mixtures, is how do you separate mixtures? And this can be something that's very easily done, or it can be something that is very difficult to do depending on what kind of mixture you're separating. So when we separate mixtures, we're going to separate them based on their different physical properties. So if you watched the live stream from last week, we talked about physical properties versus chemical properties and also physical and chemical changes. So when we're separating mixtures, we are going to take advantage of different physical properties of the components of the mixture and separate based on that. And there are a couple of very common techniques that we use. So the first one, and you have probably actually used this one, is called decanting. And this is where you carefully pour off one layer of liquid. So you can see this picture here of these two test tubes, and they've got some kind of residue down here, some kind of solid, and then a clear liquid on top. So this would be a situation if, say, you had some muddy water and you let it settle, and then you very carefully pour the water off, and you leave kind of all of the sediment, all of the mud in the bottom of either the glass or the cup, or in this case, the test tube. That would be decanting. Another common place you see decanting occur is in wine making. So when you make certain kinds of wines, you will have some solids that settle to the bottom of whatever vessel the wine happens to be in, and they will actually very carefully pour off the wine on top. They will decant it and leave all the sediment down at the bottom. So again, decanting is a really easy, very, very common technique for separating mixtures. And it works with both liquids and liquids and liquids and solids. So a liquid-liquid interaction would be like oil and water. So the oil would rise to the top and the water would be at the bottom, and you could pour the oil off. One thing I did want to point out is this is a cool little piece of glassware called a separatory funnel, sometimes called just a sep funnel. And it's a great way to take two liquids that do not dissolve in each other. We say that they are not miscible if they're going to form layers. And you can actually, instead of pouring off the top, you've got a little valve here that you can open and close, and you can allow the bottom layer to come through. So for example, you could say that this layer here was water, and maybe this was some kind of oily layer on top. You could open this valve, let all of the water drain out, and just leave the oil in the funnel there. So that's a really handy kind of chemical tool to use in the lab to separate two different liquids that, again, are not going to dissolve, are not miscible in each other. Okay, so that is one way we separate mixtures, is decanting. Another way we separate mixtures is filtration. So and this is, again, usually a liquid and a solid that you're separating. So what you're going to do is you're going to take the mixture and you're going to pour it through some kind of special paper. Usually, we call it filter paper. And so the liquid is going to pass through the paper while the solid is retained on the paper. So this is something that we use in lab a lot. Here's actually just kind of a classic setup. So you can see the solid has been left here in the funnel and the liquid is down here. This is actually a different kind of funnel. So this white area here is not actually a piece of paper. It's actually built into the funnel, but it's the same idea. The liquid passes through and the solid is left just by itself. This is something that you might do in the kitchen if you've ever, say, like juiced an orange and you have a lot of pulp in the juice and you want to get rid of the pulp. You might have taken that kind of pulp and juice mixture and poured it through like even just a paper towel, and your paper towel is your filter paper, and it collects all the pulp while allowing the juice to come through. Another kind of kitchen thing that uses filtration is if you've ever made cheese. And when you make cheese, you get a mixture of curds, which is the solid, and whey, which is the liquid. So what you do is you take that mixture of curds and whey and you pour it through cheesecloth. And the cheesecloth holds the curds, which are the solid part, and allows the whey, which is the liquid part, to drain through. So filtration sounds really fancy and very like, oh, you use this in lab, but we actually use it in the kitchen quite often as well. Okay, the last separating technique that I want to point out is distillation. So this is when you have, again, usually a mixture of liquids, although not always, and you're going to collect each based on boiling points. So you're going to have something that boils at a low temperature, it's going to boil first, and then you have something that boils at a higher temperature, it's going to come next, or, you can have, it doesn't have to be just two things, you can have mixtures of lots of things. So this is one way that you refine oil, is you separate it based on boiling points. So you really slowly heat it up and you collect everything that boils at a really low temperature first. And then you collect things that boil at higher and higher temperatures. And I've got a picture here. This is a really old classic distillation setup. You can see that they are heating a liquid here. And you can see they're trying to show like the vapor coming down into here. They've got cold water being poured onto that kind of glass bulb there, and I assume that it's in some cold water as well. And what that's going to do is it's going to take the vapor and it's going to condense it down, and you can collect it. So you can just keep this at a certain temperature and collect what you want. Then maybe you empty this bulb or you put a fresh one on, and maybe you collect the next substance that boils at a little bit higher temperature. Now, distillation is used in making like spirits. So you can take, I think they used to, when they first started purifying alcohol, like back in the Middle Ages, I want to say, they would heat up wine because they knew how to make wine. And what would happen is the alcohol would boil off first before any of the water boiled off, and they would collect that alcohol and have not a completely pure product, but a very, very close to a pure product. So this is where you get the word still coming from. It is a distillation, but still is kind of how we've shortened it, but it is a way to purify water. The other kind of distillation that separates a liquid from a solid is when you are purifying like seawater. So you can take seawater, you can heat it up, you can collect the vapor, and that is going to be your distilled water. And then what is left is the solid, is the salt. So that's a way you can take a mixture, a solution that's a mixture, and you can separate the liquid part from the solid part. Okay, it doesn't look like there are any questions. So I hope you found this helpful in terms of knowing what is a pure substance, what is a mixture, how do we classify all of these things, so that when you are learning about and reading about different things in chemistry, when they start using these terms, it's really helpful to know exactly what they mean. As always, please feel free to contact me if you have any requests for other topics that you would like to see or problems that you would like worked out. I am here. I'm ready to do whatever you guys need, especially as you potentially are starting a new semester of chemistry. And thanks so much for joining us. Talk to you later. Bye.